So it's a great pleasure to welcome Emmett Wyman from Binghamton University, speaking on spectral geometry and isometries.
Okay, thank you. Um, it's yeah, I just want to thank you for thank the organizers for inviting me to speak. And it means a lot that Carolyn Gordon reached out uh because of her work on the Can One Hear the Shape of the Drum problem, which is, widely celebrated. So um I'm really excited to talk about I'm going to talk about a similar spectral inverse problem and how it relates to the isometry group of a manifold. Okay, so first of all this is joint work with Yakun Xi, and then also there's one result which is joint work with Feng Wang and another with Xing Wang. Uh, and so all of this is shared credit. We're going to begin. The setting is going to be we're going to have a Riemannian manifold. It's going to be compact and boundaryless, typically, though sometimes we'll have a boundary. And most of what we're going to be concerned with today has to do with the Laplace-Beltrami operator and the structure of its eigenvalues and eigenfunctions, and how that relates to the geometry of the underlying space. So just to lay down some notation and conventions, because different authors have different conventions, my Laplace-Beltrami operator is going to be the negative definite operator, and it's the eigenfunctions we're going to say have eigenvalue negative lambda j squared, where lambda j is non-negative. And and this is so that lambda j corresponds more with the frequency of the standing wave with the amplitude of the eigenfunction rather than the actual eigenvalue um, of the eigenfunction. It's the Laplace-Beltrami eigenvalue. So the spectrum of the square root negative Laplacian, we're just going to say, is the collection of the lambda j's. Of course, they're repeated with multiplicity. That's important. We're not going to neglect that. And the principal question we're going to be addressing is, what does the spectral structure of the Laplace-Beltrami operator say about the isometry group of the manifold? Okay, so first, a little bit of taste of spectral geometry. Which has a long tradition. There's this beautiful relationship, this correspondence between the geometry of the manifold and the structure of its eigenfunctions and eigenvalues. Just two very, these are very big questions, big results. The first I want to present is by Deutschmann and Gilliman, and I'll just tell you about it. If the closed orbits of the geodesic flow on the cotangent bundle of your manifold are sufficiently sparse, measure 0, then the Weil law enjoys this, which estimates the number of eigenvalues less than or equal to some threshold. You have a main term, you have a remainder term. The remainder term, the standard result is a big O lambda to the n minus 1, n being the dimension of the manifold. This improves to a little o, provided you have this condition on the geodesic flow. So there's this interaction between geodesic dynamics and spectral asymptotics, which is really nice. And this is an example of perhaps a forward question in spectral geometry. And then there's also inverse problems where you ask, what does the spectrum or the eigenfunctions say about the geometry of the manifold? And we have a very well-known important question by Katz. If two manifolds are isospectral, must they be isometric? Which the problem has a long and celebrated history. I'm going to segue into a little bit of a variation on that question today, but first, to introduce the problem, let's talk a bit about manifolds with simple Laplace-Beltrami spectra and the relationship to the isometry groups. Okay, so here's the first theorem. I'll present a couple results. with proofs. First of all, the Laplace-Beltrami operator has a simple spectrum that means that all the eigenvalues have multiplicity 1, all the eigenspaces are of dimension 1, which is a very structured condition. At the same time, it's also a very common condition. It turns out that where by a result of Uhlenbeck, generic manifolds have simple Laplace-Beltrami spectra, at least generic manifolds in like a CK smoothness class. What we prove with Xing Wang and Yakun Xi is that if a closed connected Riemannian manifold has a simple Laplace-Beltrami spectrum, then its isometry group is finite. We are still in a state of disbelief that this result doesn't exist in the literature, or didn't. And in fact, we spent hours and days searching and asking, if this is already known, and we got to a point of desperation because we were still in disbelief that this wasn't already known. We asked ChatGPT once. It had the capability to actually search the internet. So at that point, when we asked it, and it hallucinated a bunch of references. But the funny thing is that my collaborator Yakun Xi and we have this sort of running joke where we'll be talking about math, we'll be coming up with some ideas or trying to discuss theorems, and we'll say, it's like, oh, well, that one's just a corollary of Steve Zeldich's 1992 paper. It's, oh, he basically already did that in 1992. This is not worth trying to do ourselves, it's already done. So the hilarious thing is that one of the papers that ChatGPT hallucinated was credited to Steve Zeldich, and was said to be published in 92. So we we had a really good chuckle over that. But yeah, it turns out that I guess I'm still in disbelief that this doesn't exist in the literature. So if anyone knows, if we've reinvented the wheel, please let me know. But it does, at least at this point, seem to be new. The proof is very indirect. It's very circuitous. I'll prove it today. At least I'll give a sketch. It's very much in the flavor of can one hear the shape of a drum, but we use the local counting function instead of the spectrum of the Laplace-Beltrami operator. And it gives you a little bit more information. And then we actually prove this by contradiction by perturbing the Riemannian metric and then constructing a contradiction that way with the uniqueness result from the spectral inverse problem. So here are some simple examples just to get acquainted. Here's a string with fixed ends, 0 to pi. It has boundary. That's okay. We don't mind. The Laplace-Beltrami operator is the standard, second derivative of calculus, and we have a really nice orthonormal basis of trigonometric functions that we can write down. This is an eigenbasis of the Laplace operator. The eigenvalue is, negative n squared. These are indexed by n from 1 to infinity. So none of these have the same, no two distinct eigenfunctions have the same eigenvalue. So the spectrum is simple. At the same time, the isometry group of the string with fixed ends is Z2. It's just the group generated by reflection over the midpoint of the string. So yeah, it's finite. It's a finite isometry group. We also have generic manifolds. Generic manifolds, by the result of Uhlenbeck before, have simple spectra. At the same time, they have trivial isometry groups. So there's a little bit of evidence, though, and I like using genericity results as, as a source of examples for things. Then there's also, of course, non-examples. you can take a flat torus, either the standard flat torus or maybe one where the corresponding lattice has, say, algebraically independent lengths. And then all of the non-trivial eigenvalues of the Laplacian are going to have a multiplicity at least 2. They're going to, if you write down the Fourier basis, then, each one comes in conjugate pair, it has a conjugate pair. And yeah, it's at least a multiplicity 2. And so it's at the same time, it has a transitive action by isometries. So, certainly not a finite isometry group. Also, the sphere. The sphere is the example that we come to a lot because it has the maximum multiplicity in some sense that you can possibly have for its Laplace-Beltrami eigenspaces. And of course, it has a very large isometry group, again, like sort of a maximal isometry group. So again, there's not going to be, it's a good negative example.
Excuse me.
Yes. Yeah.
Hi, it's Emilio Lauret. I arrived a bit late, sorry. Could you please show the previous slide?
This one?
Yes, this holds in particular for the one-dimensional torus, right? This is pretty obvious. It's the unit circle.
Yeah, that's right. It holds for the one-dimensional torus. Yeah.
And every Riemannian manifold of dimension 1, compact, connected, is isometric to a flat one-dimensional torus, right? So in particular, your result holds for dimension at least 2. Do you agree with that?
Oh, okay. Well, you can allow manifolds with boundary. So let me clarify. This theorem here, I say it's closed, and really that's just to simplify the proof. But we do prove it for just compact manifolds with smooth boundary. So you can allow, strings with fixed ends, which is this example here.
But the one-dimensional flat torus is closed, right? It's a circle.
Yeah, that's right. It's closed, and its isometry group is transitive.
Acts transitively, yes.
Yeah, so it's a large isometry group. It's not a finite isometry group.
So your result holds for dimension at least 2, right? Dimension 1 is not 2.
Oh no, it holds for dimension 1. The circle, right? If you take the circle, right? The spectrum of the Laplacian is not simple.
But you are saying it is not simple.
It's not simple, right? The spectrum.
Yes.
Right, the spectrum for the Laplacian and on the
okay.
Yeah.
No, I see. It's not a counterexample because it's not simple. There are no one-dimensional manifold. Okay, thank you.
All right. So yeah, these are negative examples that don't satisfy the hypotheses, and also don't satisfy the conclusion. Okay, so the key object that's going to drive the proof, that's going to drive the arguments, is the local while counting function. It's defined as such. You have your orthonormal basis of eigenfunctions, your EJs, and we're going to define n of x lambda, x being a point on the manifold, lambda just being a real number, a threshold. This is the sum over all lambda j less than or equal to lambda of the norm squares of the eigenfunctions evaluated at the point x. And this looks perhaps a little weird at first, but it's actually extensively studied, very natural object in spectral geometry. For example, the way that we prove the standard while law is actually first by obtaining asymptotics for the local counting function and then integrating that over the manifold. These are orthonormal, so if you integrate over the manifold, you're going to pick up 1. And then what you're going to do is you're just going to pick up 1 for each eigenfunction. Oh yeah, here, that's in the second bullet point. Another important thing to note is that this is independent of the choice of eigenbasis. It looks like it might depend on your Laplace-Beltrami eigenbasis that you set up, but it doesn't, thankfully. So this is actually a geometric object. To also emphasize that point, the local counting function is invariant under isometry. So if you have phi in the isometry group of your manifold, well, the local counting function is going to be constant on the orbits of the action of the isometry group. It's also very extensively studied, and you can derive this by just sort of writing out the physical system or the PDEs and looking at the solutions. This local counting function is precisely what you hear when you strike a drum in the shape of the manifold at the point X. So it contains a lot of, somewhat acoustic information. It's a well-studied thing. It's a natural thing. So here's a weak inverse spectral problem, and this lemma is going to help us with the proof. So we're going to suppose that M is a closed connected manifold and that G and H are two Riemannian metrics on the manifold with respect to which the Laplace-Beltrami spectra are simple, respectively. Then, if the local counting functions coincide at each point on the manifold, then the metrics are equal. And I want to emphasize that I'm not saying that the metrics are in the same isometry class. They're actually equal as tensors. So that's actually strong, even though the assumptions are strong. So the conclusion is also strong as well, and that's going to be really helpful. Okay. So I'm going to sketch the proof. The very first thing we're going to do, the proof is actually relatively simple-minded. We're going to read off an eigenbasis from the local counting functions, which is going to be easy because our spectrum is simple. There's only one eigenfunction per eigenvalue, and so we can actually just sort of read off what the eigenfunction is. Then, once we have our eigenfunctions, we can construct the heat kernel and then use heat asymptotics to recover the metric. So first, what we're going to do is we're going to, take our local counting function at threshold lambda j, and we're going to subtract our local counting function at threshold lambda j minus a small positive number, so that we only include one eigenvalue. And then we're going to take a square root, and that's exactly what absolute value of EJ is. And it's worth remarking here that the EJs are necessarily real valued, especially since the spectrum is simple and the Laplace-Beltrami operator is self-adjoint, things like this. So all we need to do is decide what the sign of EJ is, and actually all we do, perhaps to oversimplify it, is that we look at the nodal domains, and then we just take a nodal domain, give it a sign, and then every time we cross the nodal set, we flip the sign, and we just continue until we've filled up the manifold and we've given EJ of X a sign for each at each point on the manifold. And that's really it. That's how we recover the eigenfunctions. And so once we have the eigenbasis, we can write out the heat kernel spectrally as such. Right, so this is the solution kernel to the heat equation. And this is an incredibly well-studied object. In particular, its asymptotics as t goes to 0. In particular, we have Varidan's asymptotic relation, which allows us to recover the norm squared of the metric, the distance metric, between 2 points. And then, of course, once you have the distance metric, you can take the Hessian at y equals x and use that to recover the metric tensor. And so you can do this with a metric g, you can do this with a metric h, and you just follow these steps in parallel, and then what you get in the end are the same. And that's it. That's it for the lemma. Okay, so recall, what we're trying to prove is that a closed connected Riemannian manifold that has simple Laplace-Beltrami spectrum, then its isometry group is finite. And we've just proved this this lemma, which allows us to show that two metrics on a manifold are precisely equal as tensors if the local counting functions at each point are equal as functions of lambda, and the Laplace-Beltrami spectra are simple for both. We're going to use this lemma to prove the theorem using contradiction. Okay, so here's the setup. The isometry group is if the isometry group is of a compact Riemannian manifold, it's a compact Lie group. So it's finite if and only if it's zero-dimensional. So assume that dimension is 1 or higher. Then you have there's a non-trivial element in the Lie algebra, which is a non-trivial killing field on the manifold. And so we're just going to pick one. We're going to call it x. And we're going to take a generic smooth function on M. All right, so then what we're going to do is we're going to modulate the killing field by f. So we're just going to multiply it by f to change the amplitude at any given point. And if you take the flow along this modulated killing field, it's going to preserve the orbits of the isometry group. Right? It's not going to take a point out of its orbit. Right? It's still going to be it's still going to be able to be mapped from where it started to where it ended up with an isometry. However, for a generic smooth function f, this flow is not itself going to be an isometry. It's not going to preserve the metric g, right? And we can guarantee that because, you know, the isometry group is finite dimensional, and the space of smooth functions on M is infinite dimensional. So it's not too hard to pick a smooth function such that phi of t is not an isometry for most t. Okay. So now what we're going to do is we're just going to pull back the original metric tensor via the flow by time t, and we're going to call that g sub t. And again, we'll summarize that these two tensors are not in general equal, at least not for most t and for most f. And then, but at the same time, of course, because we've just pulled back the metric, phi t is an isometry from M with the GT metric to M with the G metric. So we have two claims, and after these two claims, we'll have a proof by contradiction. Right? So first of all, we claim that the local counting functions are identical at each point on the manifold and at each threshold lambda. And the second claim is that the Laplace-Beltrami spectrum associated with GT, that has simple spectrum for each t. And once we have that, the hypotheses of the lemma are satisfied, and we conclude that GT has to be identically equal to G as a metric tensor, and that's our contradiction. Okay, so claim one, extremely easy. We know that x is in the same orbit as phi t of x, orbit of the action of the isometry group. We discussed that. And then, because phi t is an isometry from M with the GT metric to M with the G metric, we have the second line of this equation. So ng of x lambda is equal to ngt of x lambda, and that's all there is about to it. To prove claim 2, this has to do with the fact that a continuous function into the integers is constant. So let lambda j of t denote the eigenvalues of square root negative Laplace-Beltrami operator with respect to metric gt. Then the number, we want to make sure that the count of eigenvalues equal to lambda, counting, in other words, counting the multiplicity of the eigenvalue lambda. This, we want to make sure that this is 1 and it stays 1, or 0 if there's nothing there. So all we're going to do is we're going to write this as an integral over the manifold of the local counting function at threshold lambda with respect to gt minus, well, the local counting function at threshold lambda minus a little bit. All right, so by claim 1, we actually know that both of these parts of the integrand are constant, at least constant in t. We also know that because we've pulled back by a function that's depends smoothly on t, that the volume element depends smoothly on t. And if the volume density depends smoothly on t, well, then this thing here, this count, is a continuous function from the real numbers into the integers. And so it has to be constant. And if it starts off at, if it's never more than 1, then it can't be anything more than 1 for any particular t. And so, again, if, because we start with a simple spectrum, once we perturb the metric, we continue to have a simple spectrum. Okay, and so that concludes the proofs of the claim and the theorem. That's it for that particular result. So I guess maybe before proceeding, I'll pause and maybe open up some space for questions if there are any. So I'll also remark that once we obtain this, we actually tried to prove this in a more direct way. We tried to prove that if you have a killing field, or we try to take a killing field on a manifold and then construct 2 linearly independent eigenfunctions of the same eigenvalue using, that were just common conjugate pairs. This works. It seems like it goes through if your killing field is non-vanishing on the whole manifold. However, of course, there are topological obstructions in general to having a manifold that admits a non-vanishing vector field. So, for example, even dimensional spheres, this argument wouldn't work for. So it's very, yeah, we're also a bit baffled that this result required such a roundabout proof. And we, after the fact, we tried to prove it directly, but then we couldn't. That's not to say that nobody can, it's just we couldn't. So I think that the last result, at least the argument, I hope establishes that there's a pretty strong connection between the local while counting function and the isometry group of a manifold. And so I'd like to explore that theme a little bit more. So here's a different yet related question. Right? We know that the local counting function is invariant under isometry. So ng of phi of x at lambda is equal to ng of x lambda, as long as phi is an isometry on the manifold. So the question is, does this characterize isometries, right? Not if it just holds for one lambda, but if it holds for all lambda. So there's sort of an infinite number of constraints to keep in mind. So put another way, if the local counting function at x coincides with the local counting function at y for all lambdas, must there be an isometry taking x to y? Must they be in the same orbit? And it has like a pleasantly musical interpretation. I mentioned before that the local counting function is what one hears is the information that one hears when you strike a drum at the point x. So another way to phrase this question is, can one hear where a drum is struck? Which is an homage to Cass's question, can one hear the shape of a drum? Except instead of trying to use the spectrum to identify the isometry class of a manifold, we're using the local while counting function to identify the isometry group of a manifold, or rather characterize the isometry group of a manifold. So, talking about this question, there are a number of positive examples. All homogeneous manifolds, all manifolds that have a transitive action by isometries, answer this question in the affirmative trivially, right? So this has to do with circles, spheres, tori, anything like this. String with fixed ends, again, it's the symmetry about the midpoint. Planar disks, the symmetries are the rotations about the origin. You can identify, in other words, you can distinguish between, you can read off the distance a point is from the center of the disk using the local counting function. In fact, just the first eigenspace is enough to do that. Rectangles and squares. Here, squares aren't rectangles in this particular context because their isometry group is different. Also, there's an REU in progress that I'm running at Binghamton, where the students are establishing that the special trigonometric triangles, so 45, 45, 90, 30, 60, 90, and equilateral triangles, that you can hear where those have been struck with Dirichlet boundary conditions. Hopefully that should be appearing this fall sometime. Tori and spheroids of revolution in R3, you can hear the scalar curvature, or rather the sectional curvature, because they're two-dimensional. And that's enough to identify a point up to symmetry. And also flat Klein bottles, you can hear where those are struck as well. So these are all the positive examples we have. We also have a generic result. This is joint work with Yakun Xi. If you have a closed manifold of dimension at least 2, it's very important that it not be dimension 1. Again, because there's not really any interesting distinction between one-dimensional circles, geometrically speaking. So if you have a closed manifold of dimension at least 2, then there exists a residual set of C-infinity Riemannian metrics for which this question holds in the affirmative. Of course, generically, the isometry group is trivial. So really what we show is that the local counting function distinguishes points generically. Separates points generically. I'm not going to go into the proof of this because it takes a bit. There's a lot of different tools involved in the proof of this one. There's transversality theory, like Thom transversality, things like this. There's also perturbations of the wave equation, Huygens principle, Duhamel's principles involved. And there's a good amount of stationary phase microlocal analysis, sort of propagation of singularities stuff going on in that direction. So there's a lot of ingredients in the proof of this one. This is perhaps my favorite of the things we've worked on, but there's another result that is a bit more time efficient. There's some negative examples as well, though. Before getting into that, let's talk about some negative examples. This is not stated as a conjecture because it simply isn't true for some examples. So there's, like mentioned before, there's a very deep literature on Cass's question, can one hear the shape of a drum? Which, of course, Carolyn Gordon is a part of. One big example is the disjoint union of Milnor's isospectral tori. I believe that you can actually find the isospectral tori down to dimension 4, but not 3. And so there's at least 4-dimensional topologically disconnected counterexamples. But in fact, there's something more. Bucer, Conway, Doyle, and Semler in a paper came up with planar domains that are not just isospectral, but that have distinguished points at which the Laplace eigenfunctions are equal, respectively, at both of those points, no matter what the eigenfunction is. So in other words, you can't hear the difference between those two things. So you can take a disjoint union of those as well. It is worth, I think, pointing out there are no known topologically connected negative examples. I'm still not brave enough to phrase that as a conjecture myself, but it's still intriguing. Perhaps there's a really high dimensional version, topologically connected negative example. So the second result that I'm going to present is has to do with what I call spectrally homogeneous manifolds. And spectrally homogeneous is in scare quotes because I don't particularly want, I'm not particularly insisting that this becomes standard language. It's just convenient for the sake of the talk, this definition. Right, so a homogeneous manifold is one whose isometry group acts transitively on the points. A spectrally homogeneous manifold is what I'll say it has a local counting function that is constant on the whole manifold for each lambda. So the question, when you ask this question, can one hear where a drum is struck of a spectrally homogeneous manifold, what you're asking is a spectrally homogeneous manifold homogeneous in the classical sense? We also like spectrally homogeneous manifolds for other reasons. In particular, they're particularly amenable to certain generalizations of Fourier uncertainty principles. The flatness you get from having a constant local while counting function is actually really convenient in that particular setting. And that has to do with joint work with Alex Josevich and Azita Maeli. But we do answer this question in dimension 2. Every closed two-dimensional spectrally homogeneous Riemannian manifold is homogeneous. Again, the proof is not too sophisticated. We use the heat kernel. We extract some local geometric information, in particular the curvature, from the local counting function. Because the local counting function is constant, the curvature is constant. And so your two-dimensional manifold is a quotient of a space form. And there's only so many different things that can be. And then you just do the casework. When it comes to the negatively curved case, we actually have to use the wave kernel, or perhaps a half-wave kernel, depending on how you like to look at it. And that will extract information that's more global in nature, having to do with the geodesic flow, or rather the geodesics. Okay, so let's first extract the local information. Again, we have this heat kernel. So the kernel of the solution operator to the heat equation, if I want to be careful about how I say that. And we're going to evaluate it on the diagonal at the point x. And on one hand, you can write it out spectrally. And then if you write it out spectrally, you can actually write it in terms of this sort of Riemann-Stieltjes integral against the local while counting function. So in other words, this quantity is audible. You can hear it when you strike the drum at the point X. At the same time, we have these really nice heat kernel asymptotics, the on-diagonal heat kernel asymptotics, where the main term's not too interesting, it's just constant, but the second term, the subprincipal term, is the coefficient is the curvature, the scalar curvature of your manifold. But because our manifold is two-dimensional, the scalar curvature is the sectional curvature, and everything becomes very, 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 very rigid very quickly. So the assumption that the manifold is two-dimensional is extremely strong. Going up in dimension, opens up all kinds of difficulties. So spectrally homogeneous manifolds are quotients of space forms. So it can be a quotient of the sphere, it can be a quotient of the flat plane, it can be a hyperbolic quotient. So we're just going to do the casework. The first two cases are easy enough. The sphere and projective sphere are both homogeneous, and we're done. The flat torus is homogeneous, and we're done in that flat case. The Klein bottle is a non-orientable quotient of the plane. And you do need to work a little bit in order to show that it's not spectrally homogeneous. Nor is it homogeneous. Well, we already know it's not homogeneous. The question is, it spectrally homogeneous? So it turns out, no, it isn't. And the way that you do this is that you actually just explicitly write down an eigenbasis. And you just take a look at what it's doing. So it's just by direct computation that you eliminate the Klein bottle. And then you have hyperbolic quotients. They can be oriented, they can be non-orientable quotients. Both cases need to be excluded because neither of those are going to be homogeneous. So here's a lemma. This is where we use the wave kernel. And I'm going to brush a whole lot of stuff under the rug here. I'm not going to prove this lemma. But if you have a hyperbolic quotient, a quotient of the hyperbolic plane by a deck group, and we take a distribution, I'm going to say this is a distribution in T. It's going to be indexed at a point X in the manifold, and it's going to be defined like this. Now, this sum definitely doesn't converge. However, you can make sense of it as a distribution by testing it against a, say, smooth or a Schwartz class function, and taking a look at what its action on Schwartz class functions is, as long as you integrate in T before you sum in J. And that's the sense in which we think about these as distributions. If we interpret it in that sense, a lot is actually known. This is singular precisely when T is either positive or negative, the length of a geodesic loop in M with endpoints at X, and this is a typo. It's just both endpoints are supposed to be at X. And the way that one proves this is by either using microlocal techniques, parametrics methods, like, for example, Bayrard, or you can use because you're working with a hyperbolic quotient, you can actually directly use Selberg's pre-trace formula. In the actual paper, we opted for the former because we did this for variable negative curvature. Because we wanted to have the lemma available for future work. So let's derive the final contradiction that we need. First of all, on a hyperbolic quotient, there are finitely many closed geodesics of minimal length. Let's call that minimal length L. The infimum of the singular support of this distribution restricted to the positive numbers is the length of the shortest geodesic loop with ends at x, as previously remarked, and is also bigger than or equal to L, with equality holding if and only if x lies along such a minimal closed geodesic. And that's because if you have a point x and you have a geodesic loop departing x and arriving at x, and it doesn't close smoothly, you can always sort of wiggle x in the direction of the angle to shorten the geodesic until it closes smoothly. And that process will shorten the geodesic. So that's exactly where this point is coming from. Then, of course, on the other hand, we've already assumed that our local counting function is constant. In other words, this infimum is constant in x, and so every point has to lie on this minimal geodesic, minimal closed geodesic, and that's just an absurdity. That cannot happen, and that's the contradiction that we derive. There's a little bit of geometry in the result, but it's not, none of it is terribly difficult. So that concludes the proof, that concludes the casework, that concludes the proof of the second theorem, and that's what I have today. Thank you for your attention. I hope you liked it.
Thank you very much for a really beautiful talk, really interesting. Are there questions?
I have a question. Do you know whether there are manifolds with only finitely many eigenvalues are not simple?
So actually so going back to the first theorem, right? This one, right? So yeah, actually, I believe that the argument does go through if a I don't want to say density zero, but density zero in some quantitative sense. If there's a density zero set of eigenvalues with multiplicity 2 or more,
Okay.
then the argument should go through. And actually, this was something that we were talking about, my collaborators and I were talking about as sort of a follow-up paper, but it never actually happened. But yeah, absolutely, I agree that it should work.
But I guess there is no any counterexample yet, so it might be zero, but
That's right.
you are able to prove that the density is zero. Okay, very nice.
Are there other questions? Let's see, the spectral homogeneity implying homogeneity, which you proved in dimension 2. I didn't catch, are there any counterexamples in higher dimension or?
Oh yeah. Again, their topology, the disjoint union of Milner's tori,
Right.
is also a counterexample to that question.
Right. That's right. Okay.
Which one? Sorry.
So the question is, so we proved that every two-dimensional spectrally homogeneous manifold is homogeneous, but the question is there a counterexample in higher dimension? And the answer is yes. At least, in fact, the first counterexample, I guess, should be in dimension 4, because there's a pair of isospectral tori that are not isometric, and they'll have the same. They'll actually have exactly the same local Weil counting function, because they're constant, and you know what the spectrum is with multiplicity and everything like this. And they'll have to have the same volume by the Weil law and things like that. At the same time, you can't take a point in one to a point in the other, with an isometry because they're just not isometric.
Mhm.
So yeah, so there might be some hope of it holding in dimension 3, but
Yeah.
but not beyond that. Yeah.
Mhm.
I
Right.
think
Sorry,
that
but this example you mean is the union of these two four-dimensional manifolds.
yeah, a disjoint union, yeah. Yeah.
Ah, okay. And connected examples?
There are no connected counterexamples
Ah, okay.
thus far.
Mhm.
There are no
Okay.
connected counterexamples to the broader question. This one, the can one hear where a drum is struck question, which is like a super question of the does the spectrally homogeneous imply homogeneous?
Let me see. Huh. Any other questions? If not, thank you again.
Well, thank you very much. Yeah. Thank you for the invitation again.